So this video is just meant to be a review of some basic differentiation and integration techniques and rules. It's not meant to prove anything or really teach new material. It should be for people who've already taken calculus and just need a quick refresher. Once I talk about it, you should be able to know what all of this is. So we'll first go over some differentiation things. So the first thing is the power rule. So if you're taking the derivative of, say, x to the n, you're going to get n to the x minus 1. So an example of this is going to be, if you take the derivative of x squared plus 2x plus 1, this is equal to 2x plus 2. And then, another rule, if you take the derivative of a to the x, this is equal to a to the x times ln of a. So an example of this is if you're taking the derivative of 2 to the x, this is going to be equal to 2 to the x times ln of 2. And a special case of this is going to be if you're taking the derivative of e to the x, which is going to be e to the x ln of e, and this cancels out to be 1. And so the derivative of e to the x is just e to the x. And then if you want to take the derivative of a log base a to the x, this is going to be 1 over x times ln of a. And so again, there's a special case if you're taking the derivative of ln of x, so base e, you get 1 over x times ln of e, which goes out to 1, so this is just equal to 1 over x. So the derivative of ln of x is just 1 over x. And then we also have some important rules. So like our product rule, so if you're taking the derivative of u times v, this is equal to u times dv dx plus v du dx. So an example of this would be if you're taking the derivative of x times e to the x. And this is going to be your first number, so x times the derivative of your second, plus your second times the derivative of your first, which is just 1. So the derivative of x e to the x is going to be x e to the x plus e to the x. And then we also have the quotient rule, which would be u over v. And this is equal to v du over dx minus u dv over dx all over v squared. And I'll come back to an example of this in just a second. I first want to show some of the trigonometric functions. So the derivative of sine of x is cosine of x. The derivative of cosine of x is negative sine of x, x not s. And the derivative of tangent of x is secant squared of x. And now I want to go back to an example for this quotient rule. So an example I actually really like is if you take the derivative of tangent, but instead of memorizing this rule, you can do the derivative of sine of x over cosine of x, because that is sine of x over cosine of x is the same thing as tangent of x. So following this rule, we're going to get cosine of x times cosine of x minus sine of x times negative sine of x all over cosine squared of x. And this is equal to cosine squared of x plus sine squared of x all over cosine squared of x. That's equal to 1. So this is equal to 1 over cosine squared of x, which is equal to secant squared of x. And so I think that's a nice little way to show, instead of just memorizing rules, you can remember the quotient rule and remember that tangent is sine over cosine, and then you don't have to remember that tangent of x is secant squared of x. And then probably the last and most important rule is a chain rule. So if you take the derivative of a function with a function inside of it, the derivative is going to be a derivative of the outside with the inside staying the same times the derivative of the inside. And so an example of this would be if you want to take the derivative of e to the x squared, this is going to be the outside, the derivative of the outside, which is kept the same, so e to the x squared times the derivative of the inside, 2x. And another example of this, because it's so useful, is if you take the derivative of cosine of 5x, so you're going to take the derivative of the outside, that's going to become negative sine of 5x, because we keep the inside the same, and the derivative of the inside, which is going to be 5. And that concludes all of our, what I want to go over for differentiation. And now we're going to go over integration. So first I want to go over just a couple properties of integrals. So if you have an integral of a dx, this is the same thing as a times the integral of dx if a is just an integer. And then if you have two different things that are added together, like du plus dv, this is equal to the integral of du plus the integral of dv. So that's just some properties, and now we'll go over some ways to actually take integrals. So first thing, there are two different types of integrals, your indefinite and definite. And so your indefinite, if you take an integral of dx, this is going to be x plus c. And that plus c is important for indefinite. And then if you take an integral of a definite, say a to b of dx, you're going to get x evaluated from a to b, which is going to be b minus a. And then, so we have the power rule, which is just, so you have an x to the n dx. This is going to be equal to x to the n plus 1 over n plus 1 plus c. So an example of this would be like if we want to take the integral of, say, 2x. So the integral of 2x dx, instead of pulling out this 2, what you can do is raise it to the second power and then divide by 2, so that's going to be equal just to x squared plus c. And then this works for all powers except for x to the negative 1. So if you have 1 over x dx, this is going to be equal to ln of x. And that should look familiar, oh, plus c. That should look familiar. If you take the derivative of this, you get 1 over x. And then if you take the integral of e to the x dx, you're just going to get e to the x plus c. Because the derivative of that just equals that. And so now I want to go over two major ways you can take integrals. So u substitution. So if you have the integral of x square root of x squared plus 1 dx, you can't just think of an antiderivative for this. And so what you can do is set u equal to x squared plus 1, and then du is going to be 2x dx. And what you're looking for is for what you have set as du to already be in there also. So all we're missing is a 2. So if we multiply by 2 inside the integral and by a half outside the integral, that's just like multiplying by 1. And then that gives us our du. So then we have a half integral of the square root of u du. And when we take this, we get a half times 2/3 at u to the 3/2 plus c. We plug that back in for u and simplify a bit, and we'll get 1/3 of x squared plus 1 to the 3/2 plus c. And now if you take integral and you're going to do u substitution with definite, like with limits, that's going to be a bit different. You can do it two different ways. So if you have the integral evaluated from 0 to 1 of e to the 9x dx. So you want to set 9x as u, so that means du is just going to be 9. And then just like before, we can plug a 9 inside and 1/9 outside the integral to get our du. And then when we evaluate this, we can either change the limits right now to u and not substitute back in, or we can keep the limits and then substitute back in. So I'm going to show both ways. So first, change the limits. So we have to change, so if x is equal to 1, when x is equal to 1, u is equal to 9, and when x is equal to 0, u is equal to 0. So we have 1/9 integral from 0 to 9 e to the u du. And so when we take this integral, we're just going to get e to the u evaluated from 0 to 9, or 1/9 e to the u evaluated from 0 to 9. We plug that in, and we're going to get 1/9 e to the 9 minus 1/9, because e to the 0 is just 1. And so if we did it the other way, and we just took straight from here, we're going to get 1/9 e to the 9x evaluated from 0 to 1. So we plugged 9x back in for u, but kept the limits. And now when we plug this back in, we're going to get 1/9 of e to the 9, because when you plug in 1, you get e to the 9, minus 1/9, because you plug in 0 again, and e to the 0 is 1. And then the next main thing to do for integration is integration by parts. And so this is a good way of getting out of integrals that you can't use trig identities for, or that you can't do just u substitution for. So a good example is this one. And so the general formula for u substitution, so you have the integral of u dv, and this is equal to uv minus the integral of v du. I was taught to remember it because it's ultraviolet voodoo. And so if we apply this to here, we could set u equal to x and dv equal to sine of x dx. So we grab both those, and now we're going to find du and v. So du is going to be dx, and v is going to be negative cosine of x. And now all we do is plug these back in and hope that that simplifies the integral. So we get negative x cosine of x minus the integral of negative cosine of x dx. And that does simplify the integral a lot, so we can do that. And this just becomes a positive. So you get negative x cosine of x plus sine of x plus c. And so I hope that this has been just a good basic review for you guys getting back into calculus.